Picture this, a bustling conference center in Honolulu, Hawaii. The air is thick with the usual academic titter, the faint scent of lease, and the hum of projectors. It's June 15, 2026, and the IEEE VLSI Symposium is in full swing. For most attendees, it's a standard event filled with papers on incrementally better silicon designs, faster transistors, and more efficient chips. But then, a joint presentation appears on the schedule. A collaboration between three titans of the semiconductor world, imec, ASML, and TSMC. Three names synonymous with the cutting edge, gathered to announce something not just new but fundamentally different. This wasn't about squeezing more from the same old recipe. It was about an announcement that would quietly, yet fundamentally, shift conversations about what the future of computing actually looks like, even as many continued to focus on the shrinking dimensions of silicon. It was the moment a decade of quiet, speculative research stepped onto the main stage. For decades, we've witnessed an almost magical acceleration in computing power, driven by the relentless shrinking of silicon transistors. Every year, devices got faster, more efficient, and smaller. This consistent progress, often called Moore's Law, became an ingrained expectation in the tech world. It felt like an unstoppable force, a natural law of the digital age, but behind the scenes, an unseen wall has been rising. Scientists and engineers have been pushing silicon to its absolute physical limits. To make transistors smaller, you have to pack more atoms into tinier spaces. Eventually, you hit a point where the fundamental properties of silicon itself start to betray you. Electrons, the very carriers of information, begin to behave unpredictably at atomic scales. Leakage current becomes a nightmare, efficiency plummets, and the benefits of shrinking begin to outweigh the costs. This isn't just about manufacturing challenges, it's about physics. The traditional scaling roadmap for silicon is undeniably slowing down, and for many, it feels like we're running out of room on the microscopic stage. What happens when the material itself can no longer keep pace with our demands for ever-increasing power and efficiency? For over a decade, whispers in the semiconductor world have spoken of a successor to silicon, something beyond the limits of our current materials science. Much of that discussion has focused on a class of materials known as 2D materials, specifically transition metal dichalcogenides, or TMDs. Imagine materials so thin, they're essentially just a few atoms thick, offering unique electronic properties that silicon, with its bulk three-dimensional structure, simply can't match. Scientists have poured countless hours into understanding how these atomically thin films could replace silicon in the most critical part of a transistor, the channel. They promised higher performance, lower power consumption, and the ability to shrink devices even further. But moving from laboratory promise to real-world application has always been the immense hurdle. The challenge wasn't just making these tiny devices work. It was making them work consistently, reliably, and at scale across vast industrial fabrication lines. The quiet unveiling of 2D material integration wasn't just a scientific curiosity. It was the culmination of decades of specialized expertise. Three major players, each a titan in their respective fields, converged to make this breakthrough possible. There's imec, the Belgian research powerhouse, known for its long-term vision and foundational work in advanced material science, consistently pushing the boundaries of what's theoretically possible. Then ASML, the Dutch giant of lithography, whose incredibly precise machines etch the microscopic pathways on every advanced chip, bringing manufacturing scalability to the impossible. And finally, TSMC, the Taiwanese foundry, responsible for producing the vast majority of the world's most advanced processors, transforming laboratory concepts into mass-produced reality. Their collaboration moved the discussion from if these materials could work to how they could be made reliable and scalable enough for mass production. It points directly to a future where silicon might no longer be the sole foundation of our digital world. The real breakthrough, the one that generated an almost palpable buzz, wasn't about a single material, but how two distinct materials could finally work together. The team revealed they had successfully integrated both N-type and P-type transistors using these 2D channels. For the N-FETs, the choice was molybdenum disulfide, or MOS2, a material scientists have been exploring for over a decade. But for the complementary PFETs, they leveraged tungsten disulfide, WS2, or tungsten diselenide, WSE2. This wasn't just a lab curiosity. It was a scalable, reliable integration demonstrated on a 300mm wafer. They achieved a world record density for complementary 2D transistors, hitting a 50-nanometer contacted poly pitch. This density, coupled with a 28-nanometer channel length printed with a single EUV exposure, placed the technology squarely within the realm of advanced silicon. The critical detail was how they engineered the flow, building the bottom contacts first, then transferring the fragile 2D channel, and finally adding the gate. This reverse approach mitigated damage and improved compatibility with advanced manufacturing, pushing 2D materials from theoretical promise into tangible hardware. For years, the promise of 2D materials felt trapped in highly specialized labs, yielding impressive but isolated results. The challenge was always moving from a single perfect transistor to an entire wafer of them, consistently. But at this Honolulu symposium, the imec ASML TSMC consortium revealed they'd cracked that exact problem. They presented a world-first, scalable, reliable integration of both N-type and P-type transistors built on 2D material channels, all on a standard 300mm wafer. This meant using molybdenum disulfide, MOS2, for the NFETs and tungsten disulfide, WS2, or tungsten diselenide, WSE2, for the PFETs. Crucially, they integrated both types side by side using a CMOS-like approach, not as individual, hand-placed components. This wasn't a fluke either. 94% of these complex 2D transistors were fully functional, pointing to a robust and repeatable process. It shifts the discussion from "is this material promising?" to "can we actually build with it at scale?" The details presented in Honolulu went beyond simply demonstrating compatible materials. They revealed an unprecedented level of integration. For the first time, researchers had successfully implemented complementary 2D transistors, using both N-type and P-type materials on a full 300mm wafer. This wasn't just a lab curiosity. The critical metric announced was a 50-nanometer contacted poly pitch, or CPP. This 50-nanometer CPP isn't just a number. It represents a world record for density in 2D transistors. To put that in perspective, it places these novel devices squarely in the performance range of today's most advanced silicon, a truly remarkable achievement for a technology once confined to theoretical discussions. This breakthrough means that, in terms of sheer transistor density, 2D materials can now compete directly with silicon at its cutting edge. Critically, this level of precision and density was achieved without the complex, multi-patterning techniques that current silicon foundries often rely on. It suggests a future where shrinking components might become simpler, rather than more intricate. Achieving such dense integration meant rethinking not just materials, but manufacturing itself. The researchers confirmed they printed the crucial 28-nanometer channel lengths using a single exposure of EUV lithography. This detail might seem technical, but it's a profound departure from the complex multi-patterning techniques often required for cutting-edge silicon. Multi-patterning involves exposing the wafer multiple times, adding layers of complexity and potential points of failure, simply to achieve smaller features. But here, with the 2D materials, the interaction of light and matter allowed for a much cleaner, direct approach to patterning. This single exposure step streamlines the manufacturing process significantly, enhancing reliability and potentially reducing costs at this particular stage. It's an elegant solution to a very granular problem, suggesting that the properties of these new materials lend themselves to more straightforward fabrication than their silicon predecessors, at least for this critical patterning step. The achievement wasn't just in the materials themselves, but in an ingenious reimagining of how these components are put together. To integrate these delicate 2D channels at such an unprecedented density, the team adopted what they call a reverse thin-film transistor flow. Instead of building from the channel up, they start by defining the electrical contacts first, etching tiny trenches and filling them with tungsten. Then, and only then, is the ultra-thin 2D material. the molybdenum disulfide or tungsten diselenide channel, carefully placed onto these pre-established contacts. The final step involves adding the gate structure, overlaying it precisely. This counterintuitive sequence dramatically improves compatibility with advanced wafer processing techniques and, critically, minimizes the potential for damage to the incredibly fragile atomic-scale 2D channel during manufacturing. This context-first approach is what unlocks the reliability necessary for scaling. This wasn't just about shrinking components. It was about ensuring they worked consistently and reliably at an unprecedented scale. The research detailed a critical success rate. 94% of the complementary 2D transistors were fully functional across the 300mm wafer. This figure wasn't a lucky accident from a single lab bench. It demonstrated genuine reproducibility and stability in the manufacturing process. Beyond just existing, these transistors performed exceptionally. They exhibited a remarkably low off-state current for both N-type and P-type devices, meaning very little power leaked when they were supposed to be off. Crucially, the ratio between the maximum and minimum current, imec and SMIN, exceeded 100,000. This metric is vital because it signifies a powerful on-off switch, critical for digital logic circuits. These aren't just laboratory curiosities. They're behaving like real-world components, laying the groundwork for what could soon move beyond experimental wafers into actual fabrication. The achievement announced in Honolulu wasn't just a fascinating material science experiment. It marked a profound shift from fundamental research to something tangible. For years, the tantalizing promise of 2D materials like molybdenum disulfide and tungsten diselenide was confined to highly specialized, almost artisanal lab settings. Demonstrations were impressive but often involved large, unwieldy contact pads or bespoke fabrication steps that simply couldn't scale to industrial production. This breakthrough fundamentally changed that conversation, showcasing a sophisticated integration and process technology. It validated that 2D devices, once merely promising as a concept, could achieve a few measurable geometry on industry-standard 300mm wafers, complete with both N-type and P-type transistors working in harmony. This rigorous engineering effort is a critical step, demonstrating a viable pathway for extending the logic scaling roadmap far beyond the silicon limits we currently face. This breakthrough, revealed in Honolulu, isn't about simply building a better silicon transistor. It's about fundamentally changing the material of the transistor channel itself. For years, the incredible properties of 2D materials like molybdenum disulfide have offered a theoretical path to ultra-scaled logic, potentially extending miniaturization beyond what silicon can achieve. The challenge has always been taking these perfect laboratory-scale results and making them work across an entire 300mm wafer with consistent performance and reliability. What we've seen is a crucial step towards this vision, showing how these 2D materials can be integrated for both ultra-scaled logic gates and even advanced applications like back-end-of-line connections or backside power delivery networks. The roadmap is now much clearer, but the journey to mass production isn't complete. While the compatibility with existing 300mm wafer processes and single-pattern EUV lithography is a huge win, the remaining hurdles involve further optimizing the manufacturing yield across diverse device types and ensuring long-term material stability in a high-volume fabrication environment. Can these materials truly move from a stunning demonstration to the heart of every next-generation chip?